the cognitive abilities.
Okay, let me continue. If people still remember when although we are not care about it, let me just quickly I want to talk about a proposal about the complete description of discrete matrix in quantum models and how it can be described given by a topological order. And as a 20% of your article. We want to emphasize the complete description means we will have some isomorphism at that level in general dimensions between these two models, and we want to hopefully reproduce the whole low energy spectrum. And we will show that this can be rigidly done in 1+1D. So, we want to care about this another description of topological orders because hopefully we want to answer some interesting questions like what are the low energy excitations that carries what representations under the symmetry, and if we symmetry the model, how will the low energy spectrum be completely changed? How can we predict those low energy spectrums? And what if the symmetry becomes non-vertical? How can we predict the low energy spectrum? And hopefully the setup can answer all these questions. And in particular, concretely, we want to show that in 1+1D quantum models, the critical points are always going to describe by some rational conformal field theories. And our goal is to find all those symmetry topological orders and use them to compute the spectrum in the presence of those symmetry defects. So let me begin with the basics, which is going to be about this isomorphism at a lattice level. I won't talk about the most general case, but only to warm you up with the simple examples. So first, this at microscopic level. So we have two sides of this correspondence. One side is this quantum model. And in the next matter, we mean that we will have a Hamiltonian. And we will have a symmetry that's some unitary operators that forms now just a group. And all those unitary operators commute with the Hamiltonian. And interestingly, we want to do a modification about the Hilbert space. Consider all those states that's symmetric under this symmetry. For example, your famous the symmetry breaking state, we will take the superposition of all the symmetry breaking states that forms a cat state, which will also live in this restricted Hilbert space. So this Hilbert space is enough to describe all the states, including those symmetry breaking ones. And simplest example is this Ising model in 1+1D in a transverse field. And Z and X are poly X and poly Z and poly X operators. And here the symmetry is the Z2 symmetry. So we only consider the states, the symmetric. Now, what's the boundary model that is isomorphic to this Ising model? It will be a boundary model of torical topological order. So just to refresh your memory, Topological is lattice model where each link we have a qubit on this 2D square lattice, and in the block this topological model Topological as the Hamiltonian of this form is the sum over two types of term, so-called vertex term and plaquette term. So this is a vertex and this is a plaquette, and the vertex term is the product of all the poly X operators on the links that neighboring the vertex and the poly, and the plaquette term is the product of all the Z operators on links that's neighboring a plaquette. And this is the block topological order. And in our setting, we consider this model with a boundary. That means we're only going to include those vertex terms and plaquette terms where have all those terms within this lattice. So we remove all those states, say this term, it looks like a vertex term, but since it's not totally within the lattice, it's removed. And then we're in a limit that this t, the coupling constant t is going to infinity. So there's no excitations in the block. But you can see that this model still have a lot of degree freedom that's on the boundary. And the boundary model is this one. So those labels the link on the boundary. So this is the 2i link, 2i plus 1 link, 2i plus 2 link, 2i plus 3 link, etc. So this term, the first term means there's a poly Z operators only at the real boundary here, a single Z operators. And this term forms this T junction type, this poly of it's a product of 3 poly operators. It's for this particular case, it will just be this kind of term. That's just because I'm drawing, but I can just draw it like with an infinite line, then all the terms will look like that. Yeah, but since the block is topological, that's just a detail we can always be like tuned. Essentially, in whichever cut, you can find such kind of a boundary model. You mean how do I know it? There's a procedure to do that. Essentially, we take the previous structure, and if it's out, we just remove it, and this term is one of the terms on the boundary. Yeah. We could add more things, but what we want to say here is this model, particular model, will be exactly mapped to the transverse Ising model. But with QI technique, you can show this isomorphism. J and H. Oh, it's a free parameter. But whichever parameter J and H will correspond to a particular parameter in the transverse Ising model. It's a 1-to-1 correspondence. And
what I see and
poly X and poly operators.
So X is anti-diagonal matrix.
Right. Right. Yeah.
There are 3.
And This model is actually a very general way of writing the boundary model because any other operators you can write on the boundary that can meet with all those fault terms going to be the other this terms or the product. So these terms are the generators of all the boundary operators you write. So this, I claim that this is an exact isomorphism. I won't show it today, but this tells us that we can say that we can call that this IP model corresponds to a topological order, which is this Topological topological order. And more generally, in any quantum model with a G symmetry in D dimension, we can find such kind of with this symmetric Hilbert space, we can find a boundary model that the block is a G gauge theory. So we can say that this symmetry topological order is the G gauge theory.
Normally, when we think of like the symmetry, and then there is a symmetry here for the symmetry of that.
It's both way works. When I say there's a quantum model D dimension, the topological order is in one high dimension. So it's D plus 1D. So when I say symmetry topological order of a quantum model, that means the topological order in one dimension or higher.
I put up this symmetry.
Right.
So,
and actually, in any models, in one models, you can actually also have more than one symmetry T, depending on what symmetry you are caring about. We'll talk about that later. There's this includes the rough boundary and smooth boundary in the limit that J equals to 0, and this is the smooth boundary, and in the limit H equals 0, this becomes the rough boundary. When you talk about rough boundary and smooth boundary, you only care about get topological boundary. And this is more general boundary that can include all possible gap and gapless boundary.
And the criterion is that.
Right. Right. So in general, it's actually a hard question to find the exact lattice model that describes the symmetry of topological order. In particular, when your symmetry can become like generalized symmetries, like high form symmetries and subsystem symmetries. And we have work on this, like for any D2 type symmetry in any dimension. Especially will include the subsystem symmetries that appear in some Ising plaquette model, and this high form symmetries, which can be we can exactly produce a lattice model that describes this its symmetry with topological orders. And just to give you a reference, I probably won't have time to describe it. So as in this matter, we're confident now that since this is isomorphism, we can think that any knowledge we want to learn about those models, we can try to learn it from this boundary of topological orders. And right. Yeah, like any correlation functions of some local operators, you can find another correlation of some operators on that model, and these two are exactly the same.
Of the boundary to be too high instead of.
Oh, because this is the simplest term I can write that still commute with the bulk terms. If I write a single z term here, it won't commute with the bulk Hamiltonian. That's the question. Horizontal z. Like this. Z2I here, it won't commute with the star term here. There's a star term here, right? Okay. Now let's try to extract some low energy physics. So we want to tune this 1D model to a critical point. In this example, it means that when a set J equals to H, that's the neural Ising critical point. And of course, pretty much we know everything about Ising models, especially we know that if you put the theory on the torus, like this is x direction and the g direction, we know the exact partial function of Ising model. And it will be formed in some low energy excitation that we can summarize as such. In particular, there are three low lying states, the vacuum state, and the two other states that's with scaling dimension 116 and 1/2. And then, as I said, that this isomorphism requires us to restrict the Hilbert space to the symmetric state. So that means that only the Z2 even the states will really appear on this boundary models. So then with this restriction, the Hamiltonian will be, the partial function is this one. Because we all know that this primary field carries the Z2 charge, but this 1/2 is Z2 even. So our claim is that this will be the partial function for this boundary model. It's an intermediate step of gauging. Gauging you restrict it and then you insert different lines and you sum over after gauging. But this we just restrict it. Yeah, we just do half steps towards gauging. Right, that's the key feature. It's on the boundary of a 2D system, but it's not a purely 1D system. Yeah, it's But when I say isomorphism, I mean these two models. But when I say that I will reproduce all the low energy physics of a model with symmetries, I will produce this pure 1D model. That's what I'm going to talk about.
So when you write on that, or model or
this is the Ising model. This equals to boundary model. Then we know when we have a symmetry and this and how do we do that? Like we can change the boundary conditions. That means on this torus, we insert a line along the time direction. That's called GT. And on top of that, we can also perform a symmetry transformation at some time slice. So that's insert a symmetry line in X direction. And then it becomes hard to predict like what is the low energy excitations when we have a symmetry defect? That's not a totally obvious question anymore. So our question is, how do we predict the spectrum with all the symmetry defect inserted? Formally, this means that we want to compute this kind of term. And that also means that given the symmetry, a complete description of CFT will be in terms of this kind of formal vector function. This is a formal basis, means that we're considering a Hilbert space with a defect line inserted and with a symmetry action at some time. And in this state, this component represents the low energy excitations in this state.
What are defects going forward along the time direction? With periodic time, operators, like operators, that's the other sector.
A time cycle means this cycle?
So on the boundary, you have time direction.
I put it in a tolerance, so I contracted.
So the practical line.
Right.
And S1 is time.
Right.
All the time is time operator.
Right.
And those
That's what I'm going to get into. My starting point is that my ball is fixed already to the topological ground state, so I don't have anyons in the bulk, and that means I don't have anyons on the boundary. I don't have a single anyon on the boundary, but I don't have like non-contractible anyon line on the boundary. All the anyons can be derived in pairs on the boundary, so that will break like two lines in the boundary, and that doesn't change. All the low energy states are still within this sector. Yes, this is the first step.
What is the
Oh yeah, this is the momentum. This is just a formal definition of partial function. Because this is the translation along the x direction. This is translation along the time direction.
and you're only taking the Hilbert space as per your inserted into
Right.
I think what you're once it's already inserted, then we don't have to do this.
okay, some over the line.
I want to do that. But let me say, from here, this is just a purely one model. And my next step is to think about this as a boundary model. So my point is that in a purely one model, as long as you have symmetry, you can perform this kind of symmetry defect twist. And the whole complete description of the CFT should be this vector partial function with all possible insertion of defect lines.
Find the state G and Gx, and which Hilbert space is that state?
GT means Hilbert space with the defect inserted here. So that means the Hilbert space.
Yes, the wrong here.
This one?
Yeah.
This is it just represents this picture. It just means that I will consider a case that in the Hilbert space, like if I have one D system as like length L, then the field at L will equal to the field at 0 up to symmetry action.
Manifold confidence.
That's the first line. Without any twist of the symmetry, I have a single partial function that's modularly invariant. But with symmetries, we can do more, right? We can, like in condensed matter, we have a 1D chain, we have system, we can literally like insert say some ferromagnetic defects and see how your low energy is changed. And then we like as a theory, we should be able to predict that case. And that case is contained in other components. Yeah. We'll reproduce all those functions. So then let's talk about the other side of correspondence. So that's a purely 1D system. Let's just set that aside and then we consider CFT appearing on the boundary of topological order. And as I say, when the topological order is in ground state, is like I'm not inserting any defect, like I'm inserting a trivial defect, then we know that this partial function only contains this kind of spectrum. Then next, we want to consider whether the topological order has any excitations. Then the picture is like this. This is my 3D topological order block, and then I insert an anion in the middle. But physically, it's never possible to create a single anion. So when I say there's a single anion in the block, that means that there will going to be an anti-anion on the boundary. So that means on this boundary 1 plus 1D space-time, there's an anti-anion defect line on the boundary. And in that case, we want to ask, what is that partial function on the boundary? So that is when we have when the CFT is coupled to the box, the complete description of all the possible low energy physics is in terms of this kind of formal partial function vector. This is a formal basis saying in the box I have a anion, and this is the particular partial low energy excitations on the boundary. And anion is sum to all possible anions in this topological order, which is usually labeled by a category C.
Function of the 3D.
Yes. It's a body topological, like body single excitation, nothing else. No dynamics in the body.
No, just bigger.
Yes. So then my claim is this vector partition function on the boundary is equivalent to this vector partition function in a purely 1D model with symmetry. Up to a basis transformation. There's a basis transformation from this formal basis to that formal basis, but all the information on the left is totally equivalent to the information on the right. Mention that symmetry topological order can give a complete description of the symmetry. And why we want to do that, because we will have, I will show you that there's an efficient way to calculate this vector partition function. And then once we know the basis transformation, we can extract this partition function with symmetry twist, which is usually hard to compute. So let me close my example of topological. So then the category is like it has 4 angles. And this boundary vector partition function have components like this. And then there's a basis transformation that can translate this vector to the IC model with the symmetry twist. So Z11. So this is IC model with the twist in both directions. It will equal to this boundary partition function. By this transformation. 0, 0. So this is the basic technique for using symmetry topological order to compute low energy spectrum of with symmetries. So now, as I claimed that this left-hand side is practically possible to compute. Let me show you how to do that.
This function is supposed to work in general.
Oh, yes, computing pairs. So, CFT twisted by topological defects, which means, well, I mean, the anion defect. So in general, we need some algebraic data about topological order. We know that topological order usually means there's a category that's describe this topological order. For example, it can be some like this. And the user data is like we can describe like how the two anions A and B diffuse into different anions. So that's like some fusion coefficients. And we want to say that how two anions, like if they fuse in different orders, what's the consistent condition? That's the F move. And then there's also this, if we take two anions, we can break them like one around another. And that's the R symbol. And this gives a complete description about the topological order. And using that, we can extract a global data that we will going to use to turn in the CFT. And that's this two data called this statistics of annuals. So two annuals, we can create them in pairs and one around the other twice in this way. That tells you the mutual statistics between the two annuals. So we call this S symbol. And you can also just create a pair of them, the same kind, and one around the other. And in this way, you can tell the self-statistics of a single annual. And you can use that to form a matrix with this entries. So we have two matrices, let's call S top and T top. That encodes all the statistical data about annuals. And then, as you have all noticed, that is not modular invariant. So what we have two numbers of observation on it. So on this boundary, you can do this literally modular transformations at the same time. You assert this formal parameter in this way. If it's purely 1D, we know that our partial function should be invariant under this transformation. And on this boundary model, what is happened is this way. Take one component, so with a single annual A in a block, it will transform as a vector in this way. So means this vector partial function, it transforms covariantly under the modular transformation. And that's a key property of boundary of topological order. And in fact, that this equation is very powerful and easy practically to use. So we just solve this equations to find what kind of symmetry can live on the boundary of a particular topological order. We do this practically.
So you ask
yeah. No, apart from first principles, but we know this rational CFT is always going to be composed by characters. So as long as we know the characters, we can extract the full Wenjie spectrum. Yeah, we can solve the solutions.
So the correspondence.
Yes, because that's an office. Yes.
What are those?
Oh, yeah, good question. So for example, we have this depth boundary, which you have mentioned, this rough boundary which we condense. And then this boundary will be this kind of vector in this basis. It means that low energy will have a single state when there's an E and R boundary. It doesn't cause any energy comparing to the vacuum state. But other states is has a finite energy gap. And this integer solution also satisfies this equation. So let me give you some bit more interesting examples. So for example, just by solving that, you can show that if your input energy TO is Z3 topological order, and you can find a solution with the smallest central charge is the statistical model 6.5 with central charge 5.4. And so you can say that this CFT has this symmetry TO. But then if your input is the S3 topological order, you'll find that the solution is still 6.5. It means that, like, depending on what symmetry you care about, this CFT can have either the Z3 symmetry topological order involve all of the S3 topological order. And we will see how they are related later if I have time. Yes, if you want to be very rigorous, but I think from some practical studies, like I think at least any of up to maybe topological order with like 40 anyons, you need to check the higher data. Like ST is not enough to this. They have some higher genus data. Actually, some kind of white hat link that to distinguish different topological orders. But for our purpose, like the anion is like lower than 40, so we don't need that. And another example is what about if CFT with anomalous Z2 symmetry. And then to check this symmetry, the input topological order is the double semion topological order. This topological order still have 4 anyons. So it has a chart that's still a boson, but like comparing to the target code, the so-called flux anion is changed to a semion semion statistic. And then just by solving that equation, we can find that this CFT can be SU2 level 1 CFT. And in terms of the vector Poisson function, it's like this. This CFT only has 2 primary fields, including vacuum. And the light spectrum is like this way. And then, as I said, there's a basis transformation from the symmetry to the topological order boundary, which I haven't described fully. But input that, we can find that this CFT twisted by this anomalous Z2 symmetry has the data as this. So there's the normal knowledge that this is a modular invariant Poisson function, and this particular state carries the Z2 charge. And then in the twisted sector, the excitations are as follows. So you can see that The V2 symmetry acts in the untwisted vectors is very normal, narrow states with a triple digit charge and -1 charge. But in the twisted vector, if you add by the V2 symmetry, one of the states carries I charge, the other states carries -I charge. So it means that in the twisted states, the Z2 symmetry U acts as -1. So it means that symmetry is fractionalized in the twisted sectors. That's the very obvious way to see that this symmetry is anomalous. Let's go. Sure.
Sorry, I have a basic question. Configuration used to be examples that you have proposed, no? Is it different from the silos or safety correspondence? The same thing.
Yeah, for chiral cases, it's reduced to the transcendent case, but this is particular for non-chiral case. Yeah, yes. But the pure 1D system with symmetries always correspond to a non-chiral topological order, always with gapable boundaries in this trivial weight class. Yeah, so it's actually the more trivial case in the classification of topological orders. Actually, it's a good time to stop.